So today I'm gonna talk about our recent work on constraints on beta functions in field theories. And this work is done with Song-Sik Lee, and the work, the archive number is here. Okay, let me start. Okay, so in the study of condensed matter or field theory, we are interested in many phases of matters and phase transitions. Thanks to the invention of renormalization group method, we are able to understand the system as a function of length scale or energy scale. From the RG point of view, most phases of matter and phase transitions are described by RG fixed points. So this leaves us two ultimate questions in this field of study. So the first one is, what's the nature of those fixed points? And secondly, what's the RG flow between those fixed points? And motivated by the second question, we focus on the RG flow in our work. Usually, in order to study the RG flow, we use the Wilsonian RG method, starting from a theory in the coupling space corresponding to one point in the coupling space. And then if we turn on a deformation or interaction term, as we lower the energy scale, the system can be described by a completely new theory corresponding to another fixed point, the IR fixed point. And the Wilsonian RG provide us a prescription to study this change. So as we integrate out the high energy mode and also do a scaling transformation for the space-time and the fields, and then we can reach the new theory. So this is very useful in the conceptual way. But in reality, due to the method is actually very complicated if we apply to a realistic theory, because during this RG transformation process, on one hand, the coupling for the existing term gets modified. And on the other hand, many other operators are generated. And if the IR fixed point is very close to the starting point, then many high-ordered operators only acquire small couplings. So this means we can do an operator truncation so that we can study the RG flow in a finite dimensional coupling space spanned by the coupling for the lower ordered operators. But this perturbative way does not always work. So in general case, the IR fixed point is very far away from our starting point. And the higher order operators can acquire very large couplings so that we cannot ignore them. So in fact, in those cases, the exact RG flow takes place in the infinite dimensional coupling space. This makes the problem of RG flow or looking
Excuse me, when you say higher order, in respect to what? To fields, derivatives, because higher order means that you are able to define a leading order, right? What is the leading order then?
So here I'm not specifying any operator. So by higher order or lower order, I only want to separate the possible operator we can keep and the possible operator we can throw away.
Different orders, right?
Yeah, okay. Exactly, yeah.
No, but related to this, may I ask you, because I did not get your initial proposal, because normally what we are talking, when we are talking about beta function, we are implying not a deformation of the theory by going to another theory. By normal beta function implies that you define coefficient of your in your theory as function of normalization point. So beta function, it is kind of dependence on the scale. So beta function is defined as dependence of coefficient in a given theory as function at the scale at which this coupling is measured.
Yes.
And your definition looks like different, so that's why I'm asking. I'm sorry.
Oh, sorry. But I don't think my proposal is different from the conventional meaning.
It's the way you formulated it. You said that you are changing, you are adding new interaction into the theory, and normal beta function, it's not a new interaction in the theory. It depends on the coefficient in a given theory, right? In the given.
Yeah, that's right. This is just a definition in Wilsonian RG. This is just a definition of beta function.
Right. That's why I'm asking. I'm sorry to interrupt.
I think maybe you are questioned about the coupling to expand the coupling space. So for the different theory, they have different operators, and they can be spanned by different couplings. Is this what you're asking?
No. It's okay. Just to give you examples of what I'm talking about. Take, say, for example, Seiberg-Witten approach. Okay, they are discussing, this particular series. Okay, and those series are two depends on the theory. First of all, they have this modular parameter. So you have not one theory, but you have the whole class of series which classified by my moduli, okay? And each module, it's a new theory. It's a new physics, right? It's not the same physics, it's different one, okay? And and at each module, you still can discuss beta function at given module as function of the scale, okay? So in this way, you can what you are discussing looks like dependence on moduli, for example, but normal beta function, it depends on the scale. It's not the same in this Seiberg-Witten example. You can see the difference. That beta function is one loop. Normal beta function is one loop beta function, and there is nothing more. But dependence on moduli is non-trivial.
Sorry, do you mean the different, like different point in the coupling space should have different beta function?
Not in the coupling space. The series classified by moduli. So moduli, it's like a different series, right? There's additional parameter in the series with moduli, and in this way, it would be different beta function. In principle, no, in this particular example I'm talking about, beta function is like this dependence on scale is one loop, and it is every time trivial. Dependence on coupling constant on moduli is non-trivial. And my impression is that you are talking about dependence on between different series. That's why I'm asking. I'm sorry to interrupt you with this.
Sorry, I don't think I fully understand your confusion.
Okay, it's the way you formulated. You said that it's different series, okay? You said that. Okay, and I'm saying that beta function, normal beta function, it's not different series. It is the same series, but dependence on the scale for coupling. Dependence on normalization point. It's not the same.
Well, I guess there is kind of confusion here, because beta function is just defined as the derivative of coupling with respect to scale. And what she was talking about is that on the flow of evolution, you generate new interaction with new couplings and new beta functions.
Right, but it's example with moduli, it's example of this kind. Dependence on moduli in Seiberg-Witten is of this type, right?
Yeah.
Sorry.
Yeah, okay. I think, so in this coupling space, like different point corresponds to different theory. And they are different by the length scale as well. Like if I lower the energy scale from one point, I will reach another theory, which has another different energy scale.
No, this is not consistent.
No, I think it's just a matter of terminology, right? You can just view the same theory defined at different length scales. Viewed at different length scales, you can just view it as different UV complete theories, right? It's just a matter of terminology, I think.
No.
Sorry, can I just interrupt? Let's maybe sorry, excuse, to not completely sidetrack the talk here, let maybe Hanma continue to talk, and we'll see. And at the end, after the talk, we can discuss more.
Yeah, maybe we can chat more later.
Yeah, no, but I disagree that it's the problem of terminology. There are different dependencies. It's dependence on moduli at one dependence, and scale is a different dependence. And so you can go along the series or you can go along the scales. It's not the same.
That's a theory flow here.
Yeah, right.
Yeah. Okay, let's use the go along the theories.
Yeah.
Rather than, okay.
Yeah, because you generate different terms in Lagrangians. It means in Lagrangian, so it means it's a flow in the theory space.
Yeah, you're right. Yeah, maybe I use the scale is just a bit not very precise. Okay. So in this general case, when the IR fixed point is very far away from the starting point, the RG flow actually takes place in the infinite dimensional coupling space. So this means, this makes the problem of RG flow or looking for the IR fixed point sounds a bit, sounds like a mission impossible. However, we can still be optimistic if we can reduce the dimension of the coupling space. So one example of this dimension reduction of the coupling space happened in the free theories. So as we know, the free theories are determined by a finite number of operators because all the composite operators can be determined by the fundamental operators. Let me give you an example. So suppose we have this phi-4 theory. And if we treat this phi square as a fundamental operator, then its composite operators, phi to the 2n, are completely determined. For example, the scaling dimension of this composite operator is given as long as the scaling dimension of phi square is given. This means the RG flow around this free fixed point is completely determined by the beta function of the source of the fundamental operator. Of course, we can write down many beta functions, but they are not independent from this one. This is a particularly good property for free theories because we can reduce the dimension of coupling space to a finite one. But its existence is not obvious in the interacting theory. So we can ask, do interacting theories have similar properties such that we can do this type of dimension reduction if we also view the operators as in two categories, the fundamental ones and the composite ones. And in this talk.
Excuse me, here I have a question. So here in the beta function, you only turn on one operator. If you turn on several operators, consider flow in the higher dimension space, then they all mixed up. It's kind of like an interacting theory.
Yes.
So,
oh, I see.
Yeah, because if you only have a phi square term in your theory, that's okay. But if you have other term, I don't know whether those there's a mixing of a flow.
So here by free theory, I mean for example, so here phi-4 theory is a little bit simple. So for other free theory, we can add a different type of mass terms, and those terms will drive the flow. But the composite operator, maybe the quartic terms are fully determined.
Okay, yeah, I see.
Yeah, around this free theory. Yes. So in this talk, I'm gonna show you that the interacting theories do have such a property. And here are our main results. So in the infinite dimensional coupling space, so there exists a measure zero subspace where the beta functions defined in such a subspace fully determines the full beta functions, which describes the whole coupling space. And secondly, we also propose an algorithm to reconstruct the full beta functions from those beta functions defined in the subspace. So I'm gonna explain these two statements in the talk.
Yeah, excuse me, yeah. So in the first point, you have an example of free theory.
Yes.
And can you, using that example, can you describe your first result? The beta function defines a subspace of coupling constant, fully determined full beta function. So what is subspace for the free theory?
Subspace. So I will.
Free theory, yeah.
So actually, I will explain those terminologies in next slide.
But in your example, your beta function is defined as differentiation over what? Over differentiation over lambda, or how you define your beta function?
Yeah, I will explain in next slide.
Okay.
Yeah. So for free theory, I think we know. Well, let me explain them through a very simple toy example. So in order to explain the terms in red and blue. Okay, suppose we have a zero dimension or ultra local theory. So the theory has action S, and it has fundamental field phi, like the phi-4 theory, we have phi as a fundamental field. And if we start from a reference theory S0, it can be deformed by, for example, operator O and its composite operators. And then by integrate out the high energy part, the couplings of those deformations can be modified. The modification is characterized in the beta functions, beta 1, 2, 3, and so on. So here I also include the beta 0 to characterize the accumulation of the free energy. So the beta function is basically, so it has our convention form dj dz, which z is the logarithm of length scale. And by beta function defined in the subspace of some coupling, I mean the beta function as a function of the coupling only, the certain coupling only, by setting other couplings 0. And the full beta functions are the beta functions sourced by every possible non-zero couplings.
Yeah, but
and
number of non-zero couplings is infinite.
Yeah, but usually we do the RG in a truncated space.
Yeah, so it's not full beta function. This is just more, I mean, wider subspace, right?
Subspace meaning we choose particular set of couplings.
Yeah, and then you extend subspace, but we're not talking about the full beta function.
Sorry?
I mean, I guess what you mean is that you define your beta function at J1 first, and then you include the higher order corrections, and then you can kind of analytically continue your beta function to higher orders. Is that what you're talking about?
I'm just define those two types of beta functions. I don't do any modification on these beta functions for now.
Okay.
Yeah.
So just to clarify, can I ask a quick question? So are you basically describing that in this coupling space, you're on the left-hand side, on the left column, you're specifying some kind of boundary conditions. You're claiming that out of this boundary conditions, you can get the full RG flow in the whole landscape? You're specifying the beta function in the red line, right? But you're saying you can, from the information of the red line, you can get the flow from the whole in the whole space.
Yeah, I think you can understand this way. Yeah, the left column is basically the boundary condition for the the full beta functions.
Yeah, so you can, do you follow you correctly when you are saying you have beta function? Generically, it's beta function would be function of all constant, G1, G2, everything, right? And then you're saying, okay, let's calculate, move along the scale. So generically, I will get beta as function of all J, I mean, J1, J2, and so on. And then you're saying, let's put all other J0, and then it would be your first line, right? And but generically, what function of all J, right?
Yes.
Okay.
Yes. Yes.
Mm-hmm.
Okay.
Okay, thank you.
Yeah, sure. So our main result actually answers the following question. So if we are given by the beta functions on the left-hand side, can we get or fully reconstruct the beta functions on the right-hand side? So those beta functions are usually we meet in the Wilsonian RG calculations. So the answer is yes, and here's my plan. So in order to explain our main results, firstly, I need to review the quantum RG method. So this is an alternative way to do the RG. And by reviewing this method, we can already get why the main result 1 is correct. And then on the other hand, the quantum RG gives another view of the RG process as a quantum evolution problem. So this changes our view of the RG problem. So if we are able to solve this quantum evolution problem, we can find the IR fixed point of the RG flow. And also we can find the full beta functions of the RG flow around the IR fixed point first, and we can do calculation to expand it until the entire coupling space. And finally, I will apply the method in step 2 and 3 to the toy example we met in the last slide. Okay, firstly, let me review the quantum RG method invented by Sonsek 10 years ago. So the main point of this method is to view the space of theory or the coupling space as a vector space, so that each point in the coupling space can correspond to a vector. And then we can do the RG transformation on the basis of this vector space. So let me go to the first point. So in order to get the corresponding vector space, we need to promote an action to a state vector. So in a coupling space, so each point corresponds to a theory. So it has an action, and the action has the fundamental field phi. So in order to do this, we firstly define an orthogonal basis labeled by this fundamental field phi. And then the vector corresponding to any action can be written as a superposition of those bases weighted by the Boltzmann weight. So in this case, for any point in the coupling space, we can find a vector written like this. And the corresponding partition function for such a theory is given by the overlap between the state vector and the identity vector. And so,
excuse me, I have a quick question to clarify something. So on the diagram on the left, J1 and J2 seem to be just numbers, just usual couplings. But when you define the action, they become functions on space. So what's happening here?
Yeah, this is, so this action and the figure is schematic, only schematic. So, and we of course can consider the coupling, the source is space-time dependent. And here in the coupling space, I don't draw any space-time dependence for simplicity. So the action written in this form is very general.
All right, thank you.
Okay, sure. And then the collection of points in the coupling space corresponds to.
But then it's not two couplings. Then what you are talking about is an infinite number of couplings. If you have j of x expanded as function of x, for example, and you have infinite number of this coupling.
Yeah, they are form factors, kind of.
Yeah. So you should define what if you are trying to make it finite, you cannot do it this way.
But we can consider a local operator, and the source for that operator can still.
No, of course you can, but then you should say that G1 and G2 are just numbers.
Yes.
Okay. Yeah, like maybe we can consider the example I gave before, the zero-dimensional or ultra-local. Yeah. Then they are numbers, and the coupling space looks like this.
Yeah. Okay. No, it's what Ilya was asking about, right?
Yeah. Thank you. Okay, then let me continue. So the collection of points in the coupling space corresponds to the collection of vectors form a vector space. So next, let me show you this collection of vectors are not linearly independent. This means we can find a set of bases for this vector space. So firstly, let us answer this question. Very simple. Are these two, so if we are given two vectors constructed by operator O and O square, so one fundamental operator and one is.
Yeah, I have a question. When you define these vectors, do you include S0 in the path integral, or there's no S0?
We can include the S0. I just, for simplicity, didn't write it.
Okay, so you should or you just can?
No, but S0 is hidden in phi, because your initial phi depends on S0, right? Because phi was a function defined for S0, right? If I following this correctly.
So I think we
this initial phi.
The S0 is the reference action we initially start with.
Yeah.
And it's usually there.
Yeah. But it's sitting in the definition of phi in this sense.
Oh.
There's sum over phi also.
Yeah, right.
Yeah, it's a function of phi. Yeah.
Yeah, I was just asking, is the S0 included in the definition of phi? Is it included in d phi?
I think it should included in the S. Otherwise, the S0 is equal to 0, which is not very physical.
Okay, good.
But then what confuses me is that you also functional integrate over phi, right? So phi is just a dummy variable.
Yeah, here. What do you mean by?
Phi is like you integrate over phi, right? So it's not a real variable, it's a dummy variable. So what you choose as phi doesn't matter since you're going to sum over all phi.
Oh, yes.
I think Hongliu's question is that this SJ1, J2, is that a complete action? So SJ1, J2 you just described is a complete action. That's it. Is that true? This SJ1, J2 is a complete action.
Yes, I think I should add a S0 here.
No, but it could be that your integration d phi is the one which depends on a 0, right? Because what means d phi? Let's say that G1, G2 equals 0. You still can discuss it, right? And then what it refers to? I think then it should be refers to a 0, right? This integration.
So here, maybe not. I'm not very clear. O1 and O2 are also function of phi.
Of course, right. But let's say that J1 and J2 equals 0. Okay. You still have integration over d phi, even at J1, J2 equals 0, right?
Yeah, that's this identity vector.
Right, but this identity should depend on a 0.
Oh, you can choose another identity like e to the s node, like as your identity.
Yeah. Okay.
Yeah.
Yeah, I see.
Okay. Okay, let me continue. So suppose we are given two vectors like this. The one is constructed by the operator O and the other one constructed by O square. So this one is the composite operator of the previous one. Are these two vectors linearly independent? So some of you in the audience maybe quickly point out that the second vector can actually be written as a linear superposition of the first one with some particular distribution of the source of the operator O. And also, you may find this familiar if you are doing the disordered problems. In those problems, you integrate over the disordered couplings. And usually a free theory is turned into an interacting theory. Here I'm doing the opposite thing. So I use the fundamental operator O to express the vector constructed by O square. So the price I pay is to sacrifice this static source, but with this dynamical source here, according to this distribution. The dynamical source fluctuates according to this distribution. And now, from this example, we can know the basis vectors are actually they can be constructed by the fundamental operators. So next, let me be more precise about fundamental operator and the composite operators. So I adopted the name from the matrix model. So the fundamental operators are actually contain one trace in the matrix model. So they are called the single trace operators. So the composite of those fundamental operators are called the multi-trace operators. So I will use those names throughout the whole talk. So this means previously we get the basis are constructed by the single trace operators. And any vector constructed by arbitrary operator can be expanded as linear superposition of those bases with particular coefficient here. So if this vector is constructed by only single trace operator only, then the coefficient is a delta function, meaning the single trace source doesn't fluctuate. But if this operator contains the multi-trace operators, then the coefficient would have a finite width, meaning the single trace source actually fluctuates. And in the language of field theory, we can actually understand this linear superposition as a projection of a theory in the entire coupling space onto the subspace of single trace coupling. So
I'm sorry, but it implies that you already made your sources to be X-dependent, right? When you are writing this relation. So when you are doing this iteration, I cannot stay with a constant coefficient, right? I mean, with fixed coefficient. My impression is that because otherwise you wouldn't construct this square or fundamental operator without having a source to be a function of X, or I'm missing something.
So suppose this source is X independent.
Yes.
Then we can still do the expansion.
Okay. No, because when you discuss this relation here, J was function of X, so that's why J1, J2 were function of X. And I'm not sure whether it's possible to do with constant J.
Sure. So all I'm talking about applies very well to the zero-dimensional ultra-local theory.
Okay. I'm sorry.
Yes. I will use that as an example later. So here, the linear superposition can be understood as a projection. So for a theory corresponding to one point in the coupling space, it will give us a finite region in the subspace of single trace coupling. And any value within this region would have a distribution according to the coefficient of the expansion. Of course, if the original point was initially within the subspace, then it will still be a point after the projection. Okay, this is the alternative understanding for the linear superposition. Actually, this linear superposition or the projection can be realized by a very standard way. Here, I give an example. So for a theory with only one type of single trace operator. So here we can write down the state vector constructed by a deformed theory, deformed by single trace operator O and its composite operators. Then we can insert an identity and also introduce two auxiliary fields. So the curly J and curly P. So the curly J's will stand for the fluctuating single trace coupling. And the curly P is identified to the single trace operator. So after a little algebra, we can write the whole formula into this form. So the form is the linear superposition of the basis with some coefficient. So later, I will also call this coefficient the wave function for this dynamical source. Okay, so far, we've learned how to view the coupling space as a vector space. And also we find the basis of such a vector space. Then we want to do the RG to the theory in the coupling space. So usually what we do in the Wilsonian RG is to do the RG transformation on the Boltzmann weight of a theory. So for an infinitesimal step of cross-graining, we can treat the RG transformation as a linear operator. So it can act on the state vector, which transform this Boltzmann weight into a new Boltzmann weight. Yeah, with the coupling change described by the beta function sourced by any possible couplings.
So
this is a full
your
beta function.
H is Hamiltonian, or what is here?
I will explain it later. Yeah, immediately.
Yeah, because it should be something kind of like dilatation in some way, right?
It it related to dilatation. It's a generator for the RG transformation.
Yeah.
I will give next step. Okay, then we can also get the partition function after the renormalization transformation, RG transformation. So the partition function is given by the overlap between the identity and the renormalized vector. And also it's an invariant quantity because the RG transformation leaves the identity vector invariant. So now let me give an example for the RG transformation and also the generator of this transformation, also called the RG Hamiltonian. So here we considered an action deformed from the Gaussian free theory. And in this case, since we do the RG transformation to modify this whole action, deformed action, then we can easily work out the generator for this transformation. It looks like this. So it's a formula and depend on the fundamental field phi and also derivative of phi.
So it's not a Hamiltonian, right?
It's not a Hamiltonian. The Hamiltonian for me is a name for it. It's a generator.
Right. But it is because it's mixed up. Because normally Hamiltonian it is a shift in coordinate, and dilatation it is not a shift, right? It's dilatation.
So this term comes from the dilatation.
Right. So in this way you can put a different letter, for example, instead of H, call it D or whatever, right? I mean, no, because it's,
yeah.
Yeah, because it has nothing to do with classical Hamiltonian, which is the generator for different things. So that's why I was confused.
What do you mean by classical Hamiltonian?
Well, as Arkady just mentioned, there must be dilatation or just energy generator in a classical sense, I mean, in quantum field theory sense. So what you have is kind of mixed up of two things.
I have quantum Hamiltonian.
It's just a name.
It's not Hamiltonian.
It's not Hamiltonian. No.
It's not Hamiltonian. You should not call it Hamiltonian.
It's not unitary to begin with.
Sorry, just to interrupt. Clearly it's just notation, but maybe more generally, let me ask the question of maybe toning down the number of questions. So Hanma can finish in time for people that need to leave at 1 p.m. And there will be plenty of time afterwards for more discussion.
Okay. Oh, I need to speed up a little bit, maybe. Okay, thanks. Let me continue. Yeah, I think it's just a name. We call it RG Hamiltonian because, and it indeed generates the RG transformation here. And then, so after review the Wilsonian RG completed by the RG transformation, we want to study this quantum RG method. It's an alternative way to do the RG. It contains 3 steps in one coarse-graining step. So firstly, we, with a given initial action, state vector, we want to project it onto the subspace of single trace coupling. And then with the wave function given by the expansion. And then we want to do the RG transformation on the basis, because it's a function of the fundamental field and the basis is constructed by operator as a function of fundamental fields. And usually this transformation will leave results in a vector out of the subspace, because the RG transformation not only modifies the existing single trace coupling, it also generates the multi-trace operators. And this whole vector is out of the subspace of single trace coupling. Then we want to project the new vector onto the single trace, the subspace of single trace source. So let me compare these two methods. So as we know, the Wilsonian RG will give us one deterministic RG path in the whole coupling space. But in the quantum RG, we do everything inside the subspace. And instead of one path, we have many paths weighted by this wave function. And it's actually a path integral of the dynamical source. So although the implementations are different in two RG method, we should get the same physical result. So the identity between the one step of Wilsonian RG and quantum RG would have 2 very important indications. So the first indication is that, so since the quantum RG method can complete it with the input of beta function sourced by single trace coupling only, then it means these beta functions actually contains all the information of the full beta functions used to complete one step of Wilsonian RG. And this is exactly our main result 1. Beta functions defined in the subspace of single trace couplings fully determines the full beta functions. And the big equality give us a second indication. So as we see, the quantum RG method take place in the subspace of single trace coupling, and it actually modifies the wave function of the single trace coupling during one step of RG. So this means we can view the RG process as a quantum evolution problem. This is actually the starting point of our main result too. We can start from this quantum evolution problem to reconstruct the full beta function. Okay, this is
a very quick question.
Sure.
So for this to be true, I think your central conclusion is that the subspace subtended by the single trace operators, they're already a complete set of the Hilbert space.
Yes.
Yeah. That's something needs to be proven, I think, right? That's what you did.
Yes, exactly.
Okay, thanks.
Okay, so with those knowledge about the quantum RG, now let's study the RG process as a quantum evolution problem. So as we see, the wave function of the single trace coupling gets evolved, and this evolution can be realized by also a linear operator generated by the so-called induced RG Hamiltonian. So I also call it Hamiltonian. It's only a name. And so here, and due to the nature of this operator, it's actually an imaginary time evolution to characterize the RG process. Let me give you an example. So as we saw before, the state vector constructed by this deformed action can be written as a linear superposition of the basis vector. And in this case, the induced RG Hamiltonian takes this form. It's a function of the beta function sourced by single trace coupling. And here, the curly J and curly P are quantum operators originates from those two auxiliary fields. And now they are canonical conjugate operators. And also there is an integration of space-time in this Hamiltonian. And the upper limit of this integration is the IR limit with at the RG time Z. This quantum evolution picture has a holographic description. So if we start from UV theory, as we do the RG, we actually generate extra dimension, which can correspond to the RG time. And the single trace coupling gets fluctuating during the RG, which is exactly the dynamical field in this one-dimensional higher bulk. And its conjugate momentum has a boundary realization as the single trace operator. Also, the wave function describe how the single trace coupling fluctuates is actually the bulk state. And the evolution of the bulk state, the quantum evolution along this RG time direction corresponds to the RG transformation of the boundary theory. So this is also an alternative realization of ADS-CFT people studied a lot. One-to-one correspond to each other. By view this RG process as a quantum evolution problem, we can make this correspondence, we can add more items to this correspondence. So if we have the induced RG Hamiltonian, I also call it RG Hamiltonian for convenience. So if it's RG time Z independent, then we can solve its spectrum and eigenstates. Suppose we are able to solve it, then the evolution problem is solved. Because starting from any initial state, we can decompose them into the eigenstates. And then we can get the information of the IR fate of the RG flow from those properties of the RG Hamiltonian. So firstly, starting from arbitrary state, the imaginary RG time evolution will always lead us to the ground state. And also on the boundary, the theory would flow to IR fixed point under the RG process. So this means the fixed point is fully characterized by the ground state of this RG Hamiltonian. And also, similarly, the local scaling operators corresponds to the excited excited state with single excitations. And the scaling dimension of scaling operators are given by the energy gap between the ground state and the excited state. And we also want to ask the OPE for those scaling operators. So since due to the nature of the eigenstates, they are complete bases, then we can expand any state with two local excitations by those eigenstates. Then in this way, we get the corresponding OPEs. Oh, oops, sorry. So with all those IR information, we are able to get a full beta function of the RG flow. Here is the result. I directly give you the result. So here is the beta function for the nth scaling operator. So Jn is a coupling of that scaling operator. And here I get the result up to the quadratic order. And of course, we can work out the higher order terms by using the information of higher ordered scaling operators and OPEs. But here we stop at the quadratic order. Let me explain those terms to you one by one. So the first term, you encode the information of scaling dimension, as we usually know. And the scaling dimension can be obtained by the the spectrum of the RG Hamiltonian, as I mentioned before. And it also shows the relevance or irrelevance of such a scaling operator. And the J star is the coupling for the IR fixed point. So where it locates in the coupling space. And also the second term comes from the scale transformation, meaning the coupling at one place can be affected by the coupling at the other place due to the scale transformation during the RG process. And the third term is the OPE, it's from the OPE. And the coefficient for this term is the OPE coefficient, which can be obtained by fuse two different excitations and to get the summation of a series of the excited states.
Well, as far as I can see this equation, I mean, the system is not closed, right? So you've got higher order couplings here.
Yeah, sure.
So you must specify the way of extracting them, otherwise you can't solve it, right?
So you mean the high order terms can be obtained by the property of higher scaling operators and OPEs, right?
Usually in things like that, you have to truncate your system, assuming something, and I suspect you've got to do the same here.
So here, yeah, exactly. So here, up to the quadratic order, I truncate at the second scaling operator of our IR.
Let's say that J are X independent, then a second term will disappear, right? But iteration over X, if J are not a constant, what means integration of, then it would be integral of your J, right? Of your coefficient from a PE, right? For constant J.
So if J is independent of X,
yeah, then
it takes another form without the integration. So I will show the form in the example.
I see.
Yeah, you can check that result. Yeah. Yeah. So here we do the truncation at the second scaling operator. But in principle, since we can get all the scaling operator as long as we can solve the RG Hamiltonian, then in principle, we can get all the higher order terms here. So in this way, we are able to get a full beta functions describing the RG flow in the entire coupling space. So of course, low order terms describe the RG flow around the stable fixed point. And then we can expand the region and to explore the bigger region in the coupling space. Okay, then let me apply this method to the toy example. So remember, we have this 0 dimension or ultra local, excuse me, toy example. And then if we are given with the beta function as a function of only the single trace coupling J1. So with those A, B, F, W are any real non-zero values. So it's an abstract 0 dimensional example. So by doing the quantum RG, integrate out the high energy part of the theory, we are able to get the RG Hamiltonian as a function of two quantum operators, curly P and curly J. And we can see that Hamiltonian is just a non-emission harmonic oscillator. Since by doing the similarity transformation, we can change it to emission Hamiltonian, then we can easily solve it. So here is the spectrum and the eigenstate. We can get any eigenstate because the bulk theory is free. And in terms of these new variables, eta, c, epsilon, we can write the eigenstate in a very usual form. But notice there are right eigenstates different from the left eigenstates because our Hamiltonian is non-emission. And then by using this spectrum and eigenstates, we are able to get the IR fate of the RG flow. Finally, we can have the beta functions around the IR fixed point. So even though the IR fixed point is can be very far away from this subspace, then we can still get the RG flow around this IR fixed point in the entire coupling space. So here is our result. We can of course compute the higher order terms, as I said before, but up to the quadratic order, the beta function for other couplings are not generated. And these two beta functions are already give very rich RG flow diagram. So there are a stable fixed point and an unstable fixed point. By tuning the parameters we design for the beta functions, we can move those fixed points around. And the two fixed points can even collide at some limit of the parameter. So the fixed point collision would qualitatively change the RG flow diagram. However, if we look at the RG flow around the subspace of J1, the RG flow doesn't change too much. So this is a very surprising result that we can reconstruct the whole flow diagram from the information of this subspace. So this comes to the conclusion of my talk today. So we have two main results. So firstly, the beta functions defined in the subspace of single trace coupling fully determines the full beta functions. And secondly, we propose an algorithm to extract the full beta functions from those beta functions defined in the subspace. So roughly, the algorithm contains 3 steps. So firstly, we derive the RG Hamiltonian by using the quantum RG method. And then we solve this Hamiltonian, either eigen equation or Schrodinger equation. And then from this solution, we can determine the IR property of the RG flow and also construct the full beta functions living in the entire coupling space. And this algorithm is applied to a one-dimensional example, a zero-dimensional example. And we also have a general d-dimensional examples in our paper. Please check it on arXiv. And since all those two models are a bit abstract, designed for this problem, we're also working on some more realistic models using this method. Thank you for your attention for today.
Thank you very much. It's very interesting. Let me stop the recording here.